Hello, I'm Park, a master's student in the Department of Artificial Intelligence at Korean University. I will now begin my project presentation. The title of the project is Pure Water, and it predicts drinkable water using machine learning. To introduce the project, the goal is to develop a machine learning model to determine drinkable water based on various water quality indicators. There are three main motivations behind this project. First, public health improvement. Access to clean drinking water is a fundamental right for all and a critical aspect of public health. However, many regions still struggle to access safe drinking water. Second, environmental protection. Water pollution is closely linked to environmental degradation, and contaminated water can cause several harm to both humans and the natural ecosystem. Finally, sustainability. The cause of pollution and water quality vary across regions, necessitating tailored management strategies that are adapted to the specific water characteristics of each area. For these reasons, we aim to develop a model using machine learning to determine drinkable water. For model development, we use the water potability dataset from Kaggle, which contains various water quality indicators. First, the trained dataset consists of 1,608 samples and is used to train the machine learning model, allowing it to learn the relationship between various water quality indicators and potability. Next, the validation dataset consists of 201 samples and is used to evaluate the model's performance during training, helping to adjust hyperparameters and prevent overfitting. Finally, the test dataset consists of 202 samples and is used to assess the model's final performance, evaluating how well the model predicts the potability of water in practice. The following is a description of the dataset composition. This dataset consists of 9 different attributes related to water quality, which will be used as input data. First is the target data potability, which indicates whether the water is safe for human consumption, will be analyzed. Now I will explain the model. First, we loaded the train and validation dataset for model training and evaluation, confirming that the train dataset has 1,608 samples and the validation dataset has 201 samples. Then we check for missing values in each feature for the data, and for convenience printed the total numbers of missing values for all features except for the first example. As a result, we confirm that there are no missing values in either the train or validation datasets. Next, we set the hyperparameters for model training and initialize XGBoost as the classification model. The reason for selecting XGBoost is that although it requires optimizing a large number of parameters, it offers both faster speed and high accuracy, while also providing powerful features such as flexibility and customization. Additionally, since there are 7 parameters to tune in XGBoost, we use random seed search CV to reduce computation time and resources. This method searches for the optimal combination of hyperparameters to optimize the model's performance. Through this process, we defined an evaluation of 50 random hyperparameter combinations to find the best one. The model's performance is evaluated through cross-validation, and the accuracy is used as the performance metric. As a result of training the XGBoost model using randomized search CV, the validation accuracy is approximately 70%, and the model's parameters were set as shown in the following table. Afterward, we loaded the test dataset and confirmed that it contains 202 samples. As in the previous steps, we also confirmed that there are no missing values in the test dataset. Using the highest performing XGBoost model, we predict the test dataset and calculated the accuracy, which was approximately 66%. Additionally, to analyze how well the model predicts each class, we calculated the confusion matrix and visualized it as a heat map. Based on the earlier confusion matrix, we generated a detailed classification report that includes precision, recur, and F1 scores for each class. Upon analysis, the model shows better performance in class 0, as evidenced by its higher precision, recur, and F1 score compared to class 1. Class 1 has a relatively low recur of 44%, meaning the model misses a significant number of true class 1 instances. This indicates an imbalance in classification performance, with the model being more effective at identifying class 0 instance. While the overall accuracy is 66% of mid-level performance, the imbalance in recur between the two classes suggests room for improvement, especially in detecting class 1 instance. Next, we visualized the ROC curve as an image, which shows how well the model classifies positive and negative classes at various thresholds. Analyzing the image, the orange solid line represents the model's ROC curve, while the blue dashes line represents the baseline for random prediction. Random prediction reflects an ROC AUC score of 50%. Therefore, with a score of approximately 69%, this indicates that it performs better than random prediction. This concludes my presentation. Thank you for listening. If you have any questions, please contact me via email. Thank you.